Hello and welcome back to the Fullerton College Pre-Press class. This is Professor Ben Kiewit. Today we're going to hopefully finish out our chapter on color management introduction. That's right, all these videos, all this chapter is just the introduction to color management. Color management deserves and gets its own class at our school and can actually be an entire career. It is a topic with seemingly no end. And that's exciting. It's got not fully defined frontiers, and that's where I like to be. Anyways, we're talking about profiles and linking using CMMs, and we're about to get into rendering intents. I also have a separate video, which I have linked through their Canvas page, so you guys can watch someone else's take on rendering intent as well as mine, to hopefully give you a more complete picture, not just my view. Anyways, the color management modules, the CMMs, which is a bit of code in most programs that deal with color, helps the computer know what colors should be shown based off the values it's given. Rather than just showing you what the values are, it interprets them for the best effect. It does that using rendering intents. They can be in lots of different places. You can have a CMM in pretty much any step in the process. And as long as you have rendering intent built into your files, if that's there, then it's going to be preserved and done appropriately to give you the best possible match with the nicest possible color. So what is rendering intent? Well, not to be morbid, but let's be morbid here. Rendering intent is kind of like the last will and testament of your color. Your color is going to die. What are its last wishes? What would it like done with its memory and its remains? Seriously, really, you take something with a gorgeous color in it, like a, I don't know, historic masterpiece painting using pigments and dyes that no longer exist on the planet, painted with gorgeous detail, and you're not going to be able to reproduce that using modern 4-color print process. Even most images you take with an RGB digital camera with very good color are not going to be able to be transformed, and not going to be able to survive the whole process into print. There are going to be things that start out looking wonderful that you love that just simply are not possible at the later stages in production. So rendering intent is a way of at least maintaining the idea of what is going on there. So there's 4 different intents: perceptual, absolute and relative colorimetric, and saturation intents. So this is a representation of a gamut. It's done as a circle to make it simple. We know it's actually more of a D shape, or the shape of a fingernail, as I like to think of it. Actually, it works well with the idea of fingerprinting a press, because it kind of looks like a fingerprint, and it's kind of what you're doing when you're figuring out what colors it prints. But anyways, this not exactly literal representation of all possible colors here in the circle. The inside circle represents what colors CMYK is capable of making. That's what a gamut is. It's colors that are possible. It's the range of possibilities. In fact, you can use it in sentences not talking about color. You can have gamuts of things that could happen to you today. Anyways, so the CMYK gamut is much smaller than the RGB gamut. The thing that's not stated, which ought to be normally, because people just kind of take RGB as the larger gamut to be somehow true to life, it still is not. RGB still struggles to capture some of the colors we're able to see with our eyeballs, especially anything that uses fluorescence or uses ultraviolet light to kind of add a little bit of something extra to it. RGB is unable to see that because the human eye is sensitive slightly beyond its visible range, slightly. Anyways, so we're going to look at how this happens. In gamut colors, if something is possible to be made both in RGB and possibly made in CMYK, you can see it inside the inner circle. This is also, in fact, by the way, a Venn diagram. But unlike most Venn diagrams, where you have 2 things that aren't related with only the similarities in between in that football shape, this Venn diagram is more of a target, because everything from the smaller gamut is possible in the larger gamut. Therefore, it's only a matter of what is beyond the inner circle that can't be done. So the out of gamut colors are numbers points 4, 5, and 6 here on the right of the circle, but 1, 2, and 3 are both achievable through, or are all achievable through both systems. So let's talk about the different intents. A saturation intent means when you have colors that are impossible to print, they all get compressed and turned into the most intense, most saturated color the same direction. It's kind of like one of those, Hollywood or bust signs you put in your car as you drive across the country to move to Hollywood and make it as a movie star finally. Well, the or bust says, or as far west on the road until your gas runs out, right? So Hollywood or bust, you left, Kansas or wherever, and you're driving across the country and you're heading straight to LA, but you run out of gas somewhere in between, and now you're forever stranded in New Mexico, but you were in the right direction. You were still pointed towards Hollywood. And that's saturation. Go as far as you can towards those colors and stop where it becomes impossible to do it. The advantage of saturation is you get to have the most saturated possible picture. The colors will be as vibrant as possible. But the downside is the relationships between the colors. Oh, I should also mention, sorry, also the in-gamut colors are moved more saturated as well to compensate for the lack of additional saturation outside. So this adjusts all the colors of the image. Not only does it bring the colors that can't be done into the closest doable color, but the ones that are able to be done are also pushed out towards the edge of the gamut and increased in saturation so that the overall image appears more vibrant rather than flattening out as it sometimes looks like it does when you convert to CMYK. Perceptual is one that I like. Perceptual attempts to compress the gamut, which is to say, take all the possible colors that you could have had and make them fit within what you're able to do. It compresses all the colors down to the final gamut, but this one also moves all the inside colors as well, but it moves them less saturated. This one is more like transposing music from one key to another, where you're trying to maintain at least a semblance, in this case, of a relationship between the colors. This says that you are identifying the colors by how they interact with each other. So all the colors need to be shifted to allow for the fact that some are not possible to be hit, but the relative differences between the colors are going to be as close to the same as they were before any change happened. Colorimetric. So relative colorimetric does not do anything to the in-gamut colors. This is kind of the least you can do, which is sometimes a good thing. Sometimes the less you touch an image, the better it turns out, right? Well, with this one, with relative colorimetric, any color that's within gamut is left alone. Any color that is out of gamut moves to the nearest possible color that can be achieved. So the differences between those three colors, 4, 5, and 6, are eradicated, and they all kind of reach the maximum of what they can be and stop there, but all the other colors stay as they were. Now, absolute colorimetric also will attempt to show you what it will look like with paper. It tries to give you a bit more of a preview of the CMYK output. So it will look grayer and duller. I don't know how well this is going to show up in a video recorded on Zoom, but here it is. You have the original image, and then the relative and absolute colorimetric changes. You can see at a glance that the relative doesn't look much different, but the absolute overall looks grayer, darker, and with less contrast, because in the real world, that's what happens when you print on paper. The top even sounds like, we're going to talk about DeltaE now. My favorite joke of the semester, really. DeltaE sounds like some sort of half-baked college fraternity. It even has a really good tagline. What are we about? We're about color tolerance here at DeltaE, bro. So DeltaE is a way of measuring the difference in color. Delta, if you remember from other sciences, typically denotes change. When you take a physics class, delta V, change in velocity, matters a lot. You're always trying to predict the throw of a ball or how far a cannonball will fly, or if you shot an arrow in the air, how high will it go before it runs out due to gravitational acceleration, blah, blah, blah. That's all delta V. But delta E is a change in, I think it's called Entwicklung. I need to look it back up to get my pronunciation correct. It's a German word for perception or experience or phenomenon. And it has no direct translation, of course, like all the best German words. Anyways, so DeltaE is about the change in the perceived color. So this is actually done mathematically inside the CLab, CIE, L star, A star, B star color model. The math at the bottom here is not nearly as complicated as it looks. It's squaring the distance between the light of the first color and the second color. Remember, you're matching two colors to each other. The A value of the two colors, the difference between those, and the B value, and it's taking it all to a 1/2 power, which is to say, simply, if you guys remember your Pythagoras theorem from like high school, or maybe even earlier, Pythagoras is figuring out how to measure the third angle, the diagonal or the hypotenuse of a right triangle. A squared plus B squared equals C squared. And that's just figuring out how long is that third line. Well, this one with L squared, A squared, and B squared equals delta E squared, you're figuring out the same type of math, but in 3 dimensions, because the lab color model is a 3-dimensional graph of color. So you're literally just doing the math to figure out how far apart the 2 points are inside the spherical grid of lab color. Now, let's just get down to some details here. Delta E, if you can get the numbers down to between 0 and 2, it's a very near perfect match, and people are not going to notice a difference. If you can get delta E down to 2, you are great. 3 to 4 is still pretty darn good, and you'll see a little bit of a difference. I do like this chart for having kind of a fairly accurate, at least a teaching model of color on the right to show you the differences between the two. 5 to 6 is okay, and 7 or more is really poor. Note that for the color class and stuff, when we're able to visit, we in the past have been able to visit the Getty and found out that their color matching for archiving and reproduction of historic arts, really they're looking for 3. 3 or better is good enough for them. And that's probably because some of the colors they're using, as we kind of mentioned, are literally extinct and exist no more on this planet except on those canvases. So there is that, but not bad for that. So 3 or better is pretty good. 2 or better is considered basically perfect. Delta E, guys. That's how we measure success in color matching. Now, to get back on the soapbox, calibration is everything. Calibration means keeping your machine maintained and running at its best. Remember, if your car has bad alignment, if it's always the same bad, if it's running as best as it can and it always leans a little bit to the right, or if you have one of those annoying shopping carts at a grocery store, which always turns a little bit to the right because one of the wheels is slightly stuck, you know that to walk down the grocery store aisle and put food in it, you have to push it a little bit harder to keep it straight. And you know exactly how much pressure to give intuitively as you push to keep it straight. But if it's a wobbly cart and it goes every which way, you got no chance, right? So keeping it consistent is it. 90% of successful color management is keeping your machines calibrated correctly. If you're not calibrated, everything else is pointless. Once again, here's our picture without color management. The designer sees all sorts of color. The photographer takes almost all of it. The pre-press removes a little more and was able to print it pretty good on digital, but by the time you get to that offset press at the end, you've lost a lot of it. And it just kind of looks less wonderful. But once you color manage properly, they all seem to agree a lot closer. Everyone understands what the output's going to be and is able to create documents and maintain documents, pass through the whole system, so you get a very near match in the final output. Remember that good color management is not about creating good color. Good color management is about passing the same color. It's about winning at the game of telephone and making it so all those changes from one to the next does not end up with do not want. All right, thanks for listening, and until next time, this has been